With that, enough geography, onto the queuing. Our first speaker is Professor Amy Ward. Amy is the Rothman Family Professor of Operations Management at the University of Chicago Booth School of Business. She is a prolific researcher in service operations management. Her work in queuing spans asymptotics, control, behavior, design, and I think, like we'll see today, some learning and data. In addition to that, she is currently the editor-in-chief of Operations Research Letters and was previously the area editor of Operations Research and the chair of the Informs Applied Probability Society. And she was also a panelist in our first session earlier today. So, Amy, with that, the floor is yours.
Okay, thank you for the generous introduction, Andrew. Thank you to the organizers. It's a really great conference, and I'm really happy to be here, so thank you. Today, I'll be talking on learning to schedule in multi-class mini server queues. So this is joint work with my colleague, John Birch, and PhD student Yu-Yang Zhang. Yu-Yang is in the audience, so we can also direct questions to her. I should say up front that I feel like I'm the one talking, but Yu-Yang is the main driver of these results, so I'm really presenting Yu-Yang's work. Okay, and so to start out, I'm going to start with a canonical model for service systems. This has been used in different parts of the literature to model data centers, to model healthcare operations, to model call centers, to model any kind of system with lots of servers where customers are impatient. So what am I looking at in this model? It has N servers, and there are J different classes. The servers are serving each class in a first in, first out manner. And there are holding costs and abandonment costs. So it's not good to keep customers waiting. And you can see that the service times could be class dependent. Now, I've purposely not given you any more information on arrival rates or service rates or abandonment rates or what those distributions are, because I don't know them. For my problem, that's something I have to learn. So I have to make scheduling decisions, meaning I have to decide this server that's free. I have to decide which class should that guy next serve, and I don't really know system parameter information. I'm interested in finite horizon costs, so I don't want the finite horizon cost to be too large. And my finite horizon cost, well, it's policy dependent. Policies should be non-preemptive, non-anticipating. So I can't kick somebody out of service and put somebody else in, and I can't know the future. And there are two components to the cost. One is a cumulative reneging. So this RJ of capital T, this is the cumulative number of class J customers to have reneged or to have left the system without receiving service up to time T. And the AJ is a per customer abandonment cost. The other term is a holding cost for queue lengths. So QJ of T is the length of the queue at time T of class J. And HJ is a per unit time, per unit job holding cost. So I said I'm interested in finite horizon cost. I actually kind of lied. I'm interested in long run average cost. And I want to have a low long run average cost. And what I'm going to compare myself to is my objective is going to be to minimize regret. And regret is defined as the regret up to time T is defined as the finite horizon cost up to time T of my policy minus the expected finite horizon cost of an optimal policy. So pi star is an optimal policy. We don't know what it is. And note that since pi star is going to be it's an optimal policy for long run average cost, for small t, this could be negative. For large t, this should be a good benchmark. Okay, so what do I have to do? I have to learn information to decide how to make these scheduling decisions. I'm not the first person to try to marry optimal control with some kind of learning problem. So the first bit here, I'm mentioning several papers that have combined statistical learning and optimal control. You can see they are an assortment of different application areas. None of these are adapted to the queuing setting. And I think there's some dynamics in the queuing setting that make things a little bit unique. More recently, we have quite a few papers that are looking at learning to schedule in queuing systems. And what separates us from these papers is these are in discrete time, but maybe more important, there's no abandonment. And so we have abandonment, and what I want you to think about, why does the abandonment matter? When I'm serving a class, I'm basically not getting abandonment from that class. So when I think about how to learn a policy, I have to really make sure that I am getting kind of uncensored abandonment samples, that I'm not mixing the scheduling policy, which impacts what abandonment samples I'm getting. So there's some kind of, I guess, confounding between the service times and the abandonment times. Because if I'm serving a class, the only guys I see abandoned from that class are those with kind of shorter abandonment times. I guess I should also mention the last two papers here are in a little bit more of a multi-agent learning framework, whereas the first papers are a little bit closer to us in the sense that there's some kind of central planner and there's no sort of multi-agent coordination aspect to it. But you can see that this is becoming a interesting area. And then some background literature. This is a scheduling problem. There's a nice book by Pinedo on different scheduling problems. I think there's a long history of academics studying scheduling problems, so this is one variant of a scheduling problem. For the learning aspect, there's connections to multi-arm bandit literature. So I've listed two classic papers in the multi-arm bandit setting. And if you think about it, pulling a bandit arm is like serving a class. So when we serve a class, you can think about that like pulling your bandit arm. The one thing I will say is that even if I'm pulling a particular arm or serving a particular class, one thing that's different from MAB literature, or at least a lot of the MAB literature, is that all of the classes are contributing to the cost, not just the arm I'm pulling. We are connected to literature of parameter estimation and queues. So we're doing this in kind of an online learning fashion, but certainly our approach here is to try to learn parameters. And from learning parameters, we are going to implement a parameter-dependent control policy. I suppose another perspective is you could try to implement a policy that is only state-dependent, that doesn't need any information of the parameters, like a longest queue first policy. So I'm not going that route. I'm going the route where I'm going to try to learn parameters and then implement some kind of parameter-dependent policy. I should also mention that there's also works not just on scheduling, but pricing in queues. And this paper here is one by Yunan Liu, and we were quite inspired by his paper because there's a lot to take in. You have to worry about the transient analysis of the queues when you do these learning problems. And so he really inspired us to try to take some of the learning literature into the queuing setting. Okay, so now with a little bit of that motivation and background, let me tell you more about exactly what I'm assuming for my model. I'm going to look at two different models. So I don't know what model is in the background. I have to learn things, but I will have a model in the background. Okay, so in one model, the background model is a time-varying MTMN plus MQ. So all of my distributions are exponential. I know my distributions are exponential. I just don't know what the parameter is. So the inter-arrival times are a Poisson process. And notice there's a T here, so it's a time-varying Poisson process. So in a lot of applications, we see that there are time-varying parameters. We want to try to be sensitive to that or motivated by those application settings. We want to try to incorporate that in our work. And then service times are exponential. Oops. And abandonment times are exponential. So what is my notation? The lambda of T, these are the arrival rates. The thetas are the abandonment rates. So 1 over theta is the mean time until a class abandons. And the mu's are the service rates. So 1 over mu is the mean time a class would spend in service. The other possibility is a background model that's a fully general situation. So I don't know anything about the distribution. I do know that in this case, I'm going to make things a little bit easier for myself, and I don't have anything time varying. So all the distributions remain constant over time. I will use the same parameters, but you can see when I don't have this lambda of T, that is an indication to you that my arrival rates are no longer time varying. They're time constant. So as I said before, my objective is to minimize regret. I'm comparing the cost of my policy to the cost of an optimal long-run average policy, that's pi star. And here I want to pause for a second. What is pi star? So let's think about this. Let me take this GGN plus G situation. So if I'm going to think about the state space of the GGN plus GQ, it's a really large state space. So I need to track, for example, for every job in service, how long has it been in service to have a Markovian state descriptor? And I also need to track for every job in queue, how long has it been in queue to know when it might abandon. So I don't think I have much hope of getting my hands easily around exploring that state space. I certainly have no hope of really understanding what an optimal policy is. So it seems like this could be a little bit tough. So the approach I'm going to take is, instead of learning an exactly optimal policy, I'm going to try to learn an asymptotically optimal policy. And that asymptotically optimal policy will turn out to be a little bit easier to learn. It's going to combine queuing asymptotics with some of these learning ideas. And maybe before I give you the outline for the rest of the talk, let me pause and make sure the model is understood. Are there any questions? Okay, so model seems to be good to go. And let's think about the outline. So I want to talk a bit more about the regret benchmark. So hopefully I've convinced you at this point that I'm working with a really challenging model. So I want to do something to give myself a little bit of an easier time. So I'm going to take, instead of trying to learn the optimal policy, an asymptotically optimal policy, and I want to talk a little bit about what that is. Then I'm going to give you an algorithm and regret bounds. Then I'll talk a little bit about empirical performance, then some current work and concluding remarks. Okay, so let's think about an asymptotically optimal policy. And the way I'm going to think about this is I am going to look at a static scheduling problem. And what I want you to do is pretend that there is no variability in the system, and pretend that customers aren't discrete entities. They just flow through the system like fluid. So I'm going to solve this static scheduling problem because I'm interested in long-run average. And the only parameters I should need to solve this are really mean information. So information about these arrival rates. And for those of you, the asymptotic I'm looking at is a fluid asymptotic for an overloaded system. The decision variable should be the long-run average fraction of server capacity devoted to class J. So if you think about this fluid asymptotic or these mean asymptotics, what I have here is the departure rate. So the departure rate of class J should be mu J, the service rate, times the fraction of service capacity I give that class. And that should be less than or equal to the arrival rate. So lambda J is the arrival rate. And basically, I can decide on what allocation of server capacity I want to each class, but of course I can't use up more than 100% of the allocation. So the sum of these BJs have to be 1. So let's think about what happens if I have an exponential system. In an exponential system, if you remember the cost, I had abandonment cost times amount that abandons, plus holding cost times amount that's in queue. So here's my abandonment cost. What should be the amount that abandons? Well, I think any of us have taught a sort of basic operations class. That's what I've written down right here. It's the difference between the arrival rate and the service rate. All the other stuff you can't serve. So lambda is the arrival rate. If BJ mu J is less than the arrival rate, then everything else must abandon. So lambda J minus BJ mu J, that's telling me at a first order level how many customers must abandon, the rate or the abandonment rate of the customers. What's the other term? Well, this is the holding term. This is very much dependent on the assumption that I have exponential reneging. And if I have exponential reneging, what should be the amount in Q? Well, lambda J minus BJ mu J, that's the amount that has to abandon. And how long is it going to sit there? Well, 1 over theta J is the mean abandonment time. So it's going to sit there for 1 over theta J time units. And this is basically the holding cost. Now, once I observe that, I realize I have a pretty nice optimization problem here. So I've split the algebra. The first term is things that do not depend on my control at all. The second term is things that do depend on my control. And if I look at the second term, this is all linear. So that suggests to me that I should have some kind of static order ranking of the classes. And that's exactly what we'll call this C mu theta policy. So C mu theta policy is ranking the classes in the order of their C mu theta. And C here is the cost. So the cost should be made up of abandonment cost per unit time plus holding cost. So you can think of the C as A theta plus H. In deference to all the literature on C mu policies, it's kind of known as C mu theta, even though I sort of have two costs, the holding cost and an abandonment cost. Okay, so the solution to this optimization problem is to rank the classes according to a static priority ranking. And when a server becomes free, I will just go down that ranking to decide what class to serve. If there is a class 1 customer available, I'll serve class 1. If there's not a class 1 customer waiting, I'll serve class 2. If there's not a class 2 customer waiting, I'll serve class 3, and so on. Okay, so that's exponential. What happens if things aren't exponential? So if things aren't exponential, well, the queue length is no longer this nice linear function of the server capacity fraction that I'm devoting to class J. Instead, there is some highly nonlinear term going on here. And I'll be a little bit easy on myself. I'll just assume the holding costs are 0. So if I have a GGN plus G situation, I'll assume the holding costs are 0. And now you notice that I can do the exact same thing I did in the MMN situation. I can split things up into one term that does not depend on the decision variables, and one term that does. And this term that does is linear in the decision variables. So I have a very nice static ranking, and it is a static ranking that I'll call the A mu policy. Now you're probably wondering, but what happens when holding costs aren't 0? When holding costs aren't 0, depending on if the distribution, the abandonment distribution is increasing failure rate or decreasing failure rate, you're going to either have some kind of static ranking solution or an interior solution. So we could think about learning that, but for the purposes of this talk, I'm not going to think about learning that. I'm going to think purely about learning one of these static rankings. Now, what do I want you to notice here? I'm proposing simple and easy to learn policies. The only thing you need to know to learn these policies is you need to learn information about the mean of the distributions. Whether it's exponential or general, I just need to learn information about the mean of the distributions. I don't need to learn any like tail information, for example. So that's much easier to learn. I should also credit, there's a lot of literature on these AO results, on the asymptotic optimality results. So to make this rigorous, Mandelbaum and Stoyer and Gervich and Witt, these are nice papers that looked at the asymptotic optimality for C mu without abandonments. This first Attar paper, Attar and his co-authors looked at asymptotic optimality of the MMN plus M situation. This next Attar paper, Attar, Kasky, and Shimkin, they have exponential abandonment, but general interarrival and service times. And this Long et al. Paper, so this Long et al. Paper has general abandonments, but exponential service times. We don't have the asymptotic optimality for a fully general system, but we do have convergence results, and this is in this Puha and Ward paper. It also sets up the invariant states of the fluid model, which inspire this problem. So if you want to know more about this Q function, you want to look at the Puha and Ward paper. Okay, so I'm resting on the giants of a lot of people that have studied these results in the literature. Now, I don't know if anybody noticed, but I dropped off the T in my exponential case. So how am I bringing the T back in, the time varying bit? I want you to notice that the ordering here does not depend on the arrival rate. So it seems to be a sensible thing to do that these policies should work pretty well when I have time varying arrival rates, because certainly the policy doesn't depend on the arrival rate. Now, I'll say there's one caveat to that, because you have to worry a little bit about, you can't quite save customers because customers could renege. I'm not going to say more about that right now. You can either ask me a question about it or we can talk about it offline. what I want you to notice for this slide is that because the ordering does not depend on the arrival rate, it seems natural to think about, oh, okay, so maybe I can add time varying arrival rates into this model. Oh, and I think I mentioned that this was an overloaded regime. So I wanted to add, this is relevant for overloaded systems because if you look at my optimization problem, if I don't have an overloaded situation, meaning if I have enough capacity to solve everybody, then your optimal solution is to set Bj equal to lambda j mu j for all of your classes, and you have exactly 0 as the solution to your optimization problem. What you're really doing here, I'm forcing you in the overloaded situation to choose which of the classes that are most important to serve. And I'll also make the argument that that's when scheduling is probably most important. Any questions on what the asymptotically optimal policy is? Because this is the policy we're going to try to learn. Okay. Okay, so one thing you're probably thinking is if I'm going to tell you I'm not going to learn optimal policy, I'm going to learn this nice C mu theta static ranking policy, how well does it do? So let's just look at the performance. So I have 2 graphs, and the 2 graphs I'm looking at, one has 2 classes, one has 4 classes. It's a purely exponential system, no time varying, and this is small enough that I can just do the MDP analysis numerically and calculate an optimal policy. And what you're seeing on the graphs is the x-axis is the simulation time, the y-axis is the percentage error off of optimal. And you know, if I have 2 servers, I don't do that well. But if I have 8 or 16 servers, I'm doing quite well. So the point I'm trying to make to you is if I have, let's say, 10 servers, on the order of 10 servers, I'm not losing very much by trying to learn the C mu theta rule. What is the C mu theta rule, rather than trying to learn the exactly optimal policy? I'm also referencing this paper down here by Down and Kuhl and Lewis, and we know that static ranking isn't always optimal because they have, for j equals 2 customers, they solve the MDP and they show you the threshold policy, state-dependent threshold policy can be optimal, at least under certain parameter situations. Okay, but as I get more servers, even if, as I get more servers, the policy becomes pretty close, so the performance becomes pretty close to this nice static ranking asymptotically optimal. All right, so updated.
Excuse me, Amy. Peter
Yes.
here. I've just got a quick question about that last slide, if you don't mind. Is that okay?
Yes, of course.
So you said for the small numbers, you actually could work out the optimal policy, and the performance of the policy looks the same. Did the actual policy itself look like a C mu theta?
Oh, that's a good question. We numerically computed the optimal policy. I don't believe it looked exactly like C mu theta. I'm gonna, Yang, do you remember? Okay, so I don't believe the policy was exactly C mu theta, but it was something close to C mu theta. And so what happens is in the part of the state space where I'm spending most of the time, I'm making the same decisions. But my memory is that when we numerically computed the solution to that MDP, it didn't exactly give you a static ranking. So I'm not claiming that for a finite n, I would have exactly the same policy. I'm just claiming that a policy that's not quite C mu theta would be performing pretty close to it.
Okay, thanks.
Okay, so that means that if my objective is to minimize regret, instead of comparing against an optimal policy, I'm going to compare against the C mu theta policy. And notice that I am now fixing in. So if we wanted to make something rigorous for the asymptotic optimality, I'd be taking n to infinity. I'm not doing that. I'm fixing in, and my regret results are going to be for a fixed n, we're worried about what happens when t gets large. So analysis assumptions, the arrival rates, I'm going to assume that they're bounded between some lower lower bound and upper bound, and the lower bound needs to be bounded away from 0. So these are some finite constants. I don't necessarily know them. If I know them, I'll be able to give you better regret bounds, but I don't assume that I know them. I also need some kind of index separation. So if I'm going to try to learn these, you can imagine that the larger separated the indexes are, the easier learning problem I have. The closer together the indexes are, the sort of more samples I need to learn. Okay, so then let me give you my algorithm and regret bounds. So first of all, let's look at a lower bound on regret. So I said we could think of this like the multi-arm banded literature in the sense that pulling an arm is like serving a class. So if you think about the multi-arm banded literature, we know that a lower bound on regret is like log t. So you should not be too surprised to see that my lower bound on regret in this problem is also some constant times log t. And so what I meant here is that if you have upper and lower bounds that you know on your parameters, then I could specify what that c is. Otherwise, you just have to know that the growth rate is something like log t. And the way I'm writing these results is I'm kind of writing the result, but if I move to the GGN plus G situation, I'm going to need to require additional assumptions. So for example, I would need to require that I have finite exponential moments on interrival and service distributions. Okay, so basically I'm looking at set of policies. The set of policies I'm looking at, you think about static priority rankings. And it's basically any static priority ranking. I could randomize over the static priority rankings. I could do some idling. I could say something like serve class 1, then class 2, and then serve nobody. So any type of policy like that is fair game because I'm trying to learn this static ranking policy. Okay, so that gives me something to go for. I want to find an algorithm that gives me something like log t regret. I'm going to look at an algorithm that has a learning phase and then an exploitation phase. So what happens? The learning phase will be up to time tau. And in the learning phase, I'm going to collect samples. So I'm going to divide the learning phase into capital J different cycles. And during each cycle, so for example, in cycle 1, I will only serve class 1 customers. So I will only serve class 1 customers. And that means that I'll take abandonment samples from everywhere but class 1. So I'm doing this very deliberately, is that if I have customers from any classes 2 through J, I won't serve them. I know that's a little bit wasteful, but I'm purposely doing that because I want to make sure that I get uncensored abandonment estimates. And so that means from classes 2 to J, I'm getting the estimates of the abandonment times, and they're essentially uncensored. I say essentially because maybe they're cut off at tau over J when I switch to a different policy, but I can correct for that pretty easily. Whereas I can't quite correct for if I'm serving class 1 and I have abandonments, how do I correct for the fact that I had some censoring going on there? I will collect service completions for all classes. Obviously, most of the service completions are from class 1. But maybe I had an initial distribution where there were some guys in service from other classes, or when I move from cycle 1 to cycle 2, maybe I will still have some people in service from class 1. I might as well collect their service times in cycle 2. Okay, so each cycle, I'm only serving 1 class. I'm collecting abandonment samples from the classes that I'm not serving. I'm collecting service completions from all of the classes. And then at time tau, I'm going to form estimates of the mean, of the mu, and the theta. That means I will now have a C mu hat theta hat rule. And during the exploitation phase, I will serve customers according to the C mu hat theta hat rule. What we hope, if I collect enough samples, I should have, with high probability, that C mu hat theta hat rule is exactly the C mu theta rule. And I have an upper bound on regret. So my upper bound on regret is that there exists some finite constant C such that the regret of my LTS, so this is learn then schedule policy, is less than or equal to C times log T. I am sure that I could get that constant to be a little bit better. Maybe if I did a little bit more adaptivity in my learning, maybe if I did something a little bit smarter in terms of not dedicating service to only one class. However, since I have these log T bounds matching, we felt like this was a pretty good place to be. So I have this lower bound on regret that's log T, upper bound that's log T, so my order matches. Now, how do I do the regret analysis? So I want to touch a little bit on the proof because I think the framework makes a little bit of sense. So I'm splitting the regret into regret incurred during the learning phase. So that's regret incurred between time 0 and time tau, and regret incurred during the exploitation phase. The regret incurred during the learning phase is quite easy. So if I don't serve anybody, I have an easy upper bound on regret that would be linear in tau. And what you see is the upper bound on the arrival rate. And then this is basically the cost, assuming everybody's abandoning. And this is the cost of the abandonment and then the cost of holding them there. So this is basically, I don't serve anybody. It gives me a pretty easy upper bound on this learning regret. The exploitation regret is a little bit more difficult. So in the exploitation phase, I have a regret that is something like this exponential e to the negative L1 times tau. So L1 here is some constant that I could write out in terms of those parameters if I knew them or if I had upper bounds on them, but I'm not writing them out on this slide. And the way I'm getting the log is that I'm equating the right-hand sides of these two inequalities. And if you equate the right-hand sides of these two inequalities, you'll see that you want tau to be log T. So what about this exploitation regret? This is now where the meat of the analysis is. So if I think about the exploitation regret, what can happen? Well, I got things right. And if I got things right, I need to look at the exploitation regret when at time tau, so at time tau, I am using exactly the C mu theta policy. So where is this regret coming from? Well, the regret's coming from the fact that if you look at time 0, I've got one, and I start running a system with C mu theta, versus time 0, I start running a system with a learn then schedule policy. At time tau, they'll have different initial states. So I'm going to need to make sure that even though I'm running the same two policies starting at time tau, that these systems sort of converge pretty quickly to being the same thing. So I need some kind of exponential loss of memory. Okay, so what I'm saying here is this probability should be pretty high, should be pretty close to 1, and I should just need to worry about this. And so that's giving me this term here. For here, this is what happens. Well, the other thing that can happen is I didn't learn the policy correctly. And I'm hoping, and that should occur with pretty low probability. So I'm hoping that this term is going to be pretty small. And then this term, I'm not going to have too much control over because I'm running the wrong policy. Okay, so each of these 3 different terms. So this one, this exploitation, I'm basically relying on some kind of weak ergodicity result or some kind of exponential loss of memory because I've got 2 systems, they're running the same policy, but they've got different states at time tau. This probability, this is really about the estimation performance. So assuming I'm collecting enough samples, then the probability that I learn the wrong policy so that my empiric C mu hat theta hat rule is the same thing, is not the same thing as the C mu theta rule, that should be pretty small probability. And that's something like exponential of negative tau. And then I have this last term, and we have a pretty nice bound on the Q length that comes just from the fact that, well, we have these abandonments. So if you don't serve anybody, it's never going to get too large. So if I combine all of these things, that tells me that this exploitation regret should be decaying pretty quickly, decaying like what I showed you in the last slide. And that will give me my log T bounds ultimately. So just an overview of everything that's happened here. We had this overall regret. We divided it into exploitation and learning. And the exploitation regret, we had to deal with either I learned the policy correctly or I didn't. If I learned the policy correctly, I need to rely on some kind of weak ergodicity results. So I need to deal with the fact that there's this transient phase going on in the queue. And if I didn't learn the policy correctly, well, that should happen with pretty low probability. So here I'm relying on results on estimator performance. So that's sort of the idea of how everything is being glued together. Any questions? Okay, so let's go on. So I've given you a lot about the theory. And if you like the proof, excellent. If you got a little bit lost in the proof, no worries. I'm going to talk about the empirical performance. So what I want you to think about right now is, what are we doing? I've proposed a policy to you. It's called the Learn Then Schedule policy. What I want you to do is, for some amount of time tau, basically log t amount of time, I want you to collect samples. Then we're going to estimate this C mu hat theta hat policy. Then you're going to run your system according to this C mu hat theta hat rule, and let's see how it performs. Okay, so the first slides I'm showing you, this is actually exactly the same setup that I showed you earlier. I have two classes. Everything is exponential, so I'm looking at a setting where I can calculate the exact optimal MDT policy to give myself some comparison benchmarks. What am I showing you? Oops. The x-axis is time, and the y-axis is percentage increase from optimal. And so I'm doing two things. This blue line is the cost of my Learn Then Schedule policy minus the cost of the optimal policy, which I can numerically compute, divided by cost of optimal. And the orange line is comparing the C mu theta policy to the optimal policy. And this repeats a little bit what you saw before, which is basically, if I only have two servers, I'm getting a fair bit of error because C mu theta is really not the optimal policy. When n equals 8, I'm getting much less error. And what you can see is, if I look at the error between this Learn Then Schedule and the optimal policy, it's kind of looking like a log growth rate. Okay, so the theoretical result said my regret should grow something like log t. That's sort of what you're seeing here. Or that is what you're seeing here. Okay, so n equals 8 is kind of a better situation for me, because now it says that, okay, my asymptotically optimal policy is performing pretty well. So let's try to learn the asymptotically optimal policy. Let's make things a little bit more challenging. So instead of inter-arrival times being Poisson, let's make the inter-arrival times be Poisson with an intensity function that is fluctuating over time. So the intensity function is periodic. And I'm plotting the regret. I have 3 different curves. The curves I'm showing you, so the service and the patient's times are still exponential, but the arrival rates are some sine function, and the amplitude of the sine function is growing. So there is more variability for the arrivals in the green than there is for the orange than there is for the blue. And if I let you pause and stare at this graph for a little bit, you'll notice that the regret is largest for the blue. So the regret is largest for the arrival, for the situation where I have the most variability in the arrivals. Any ideas why? Because I usually think of variability as being a bit bad in queuing situations. Okay, so I'm not going to 100% say that I know why, but let me tell you what our working hypothesis is. Our working hypothesis is what's happening is most of the cost is being incurred in the learning phase. So most of the cost is being incurred early on in this learning phase. During the learning phase, what does my policy do? It says, well, for a bit of time, I'm going to serve class 1 only, and I'm going to let class 2 abandon. And for a bit of time, I'm going to serve class 2 only, and I'm going to let class 1 abandon. Now, if I look at my cost function, class 2 abandoning, well, that's where that's kind of the highest cost. This class 2 abandonment cost is pretty high. So things abandoning are going to give me cost in this situation. Now, let me think about what happens when I'm not serving class 2. When I'm not when I'm not serving class 2. I'm serving class 1, I'm not serving class 2. When I'm not serving class 2 is basically operating like an infinite server queue. So class 2, things come in, and the abandonments are basically like an infinite server queue. So if I have an infinite server queue and I have more variability in that infinite server queue, well, more variability means there's going to be more guys in the system and less guys departing. Less guys departing for me means less abandonments. Less abandonments, well, abandonments is exactly where that cost is, where most of my cost is residing. So that suggests that maybe it's the variable that will give me the lowest cost, and that is exactly what I'm seeing here. So I do not believe that this result is robust. I think if you change the parameters, you're going to get different orderings. Okay, so another thing we might want to do is instead of exponential patience times, we should look at other types of distributions. So here I'm looking at different distributions. I've got uniform, gamma, and Pareto. I have them ordered in terms of the variability of the distribution. Notice that this most variable distribution has infinite variance, so we can handle infinite variance distributions. And here you can see that there doesn't seem to be any relationship between what the regret is and how variable the distribution is. It's just kind of all over the place, so can't really say anything there. What you can notice in both pictures is that the regret is kind of growing like this log t, and that's kind of what that is what our results predict. If you're looking for an open problem, one thing we don't have is time varying arrivals and general distributions on the abandonment. And these results I'm showing you here have time varying in the arrivals, but the abandonment distributions are quite general. So we don't have proofs in that situation, but we do conjecture, and numerically it looks like you should be able to handle situations where you have general abandonments, general service time, and some kind of time varying in your arrivals. Okay, so empiric performance, I'm getting to the last part of my talk. That's the current work and concluding remarks. Okay, so some current work is instance independent regret. So one of the things that you might be wanting to look at is minimax regret. So this is, I'm taking the soup over the entire parameter space here. So this is the regret that I've shown you. This is the difference between my policy and an asymptotically optimal policy. And now I want to take the soup over the entire parameter space. And I'll say working theorem because Yu Yang's done some here, but maybe I'm not quite confident enough to put theorem there. But the first thing we observe is learn and schedule is probably not enough. We probably need to do something a little bit better. And that's because this minimax regret looks like it's growing at sort of t to the 2/3, but a lower bound should be sort of order square root t. Now, what might I want to do to try to do a bit better? So one of the things you might have noticed is that there's not a lot of adaptivity in my policy. In the policy I gave you, I basically learn for a period of time, and then I start doing the schedule. And I'm not really doing any adaptive type of learning. So one way you might think about making that policy better is to try to do some adaptive learning. So our proposed algorithm here is some kind of phased UCB. And so what do I mean by a phased UCB? So we're still going to keep this warm-up period. And I'm keeping the warm-up period because I want to start out with estimates on my abandonment parameters or my abandonment means that are, I'll call them unsullied with service time estimates. So I'll have my warm-up period. Then I have these different phases. The phases, this is sort of linked 2 and then linked 2 squared. And then in general phase K should be sort of linked 2 to the K. At the end of each period, I can update my estimate on the mu and the theta parameter according to some kind of upper confidence bound. And I guess I said upper confidence bound, but it's really a C mu divided by theta policy. So the theta should be probably a lower confidence bound and the mu should be sort of an upper confidence bound. Now, you might think that that's enough. I'm not quite sure that's enough because we think there may need to be some forced exploration there. And that goes back to the fact that if you think about it, if you have this C mu theta policy, and I say, okay, I'm going to serve class 1, I'm going to serve class 2, class 3, maybe I sometimes serve, and classes 4 and 5, I never serve. So what does that mean? That means that in all of these periods during the exploitation phase, I'm not going to see abandonments from classes 1 and 2. I may see some abandonments from class 3, and then class 4 and 5, I'm going to see abandonments from. But that means I'm not really going to be updating the estimates for the abandonment mean for class 1 and 2. And so that's why our guess is you're going to need to do something a little bit smarter than just updating your estimates at the end of each phase. You will probably need to do some kind of forced exploration. So that's kind of current work that we're thinking about. Okay, so that brings me to kind of the end of the talk. I think the organizers are asked to leave time for questions. So I'm leaving, I don't know, 5 to 10 minutes for questions and for us to discuss. But let me give you just a little bit of conclusion first. So summary, what have we done? We've solved the learning variant of a canonical scheduling problem in a multi-class mini server queue with abandonment when model parameters are a priori unknown. We propose an online algorithm which achieves the optimal regret of O of log t, and optimal, I mean up to order, not counting constants. Follow-on work, so we're thinking about this instance-independent regret. And then I thought maybe I'd just list several kind of open problems for people if you're looking for something to think about. So one open problem is we still need asymptotic optimality results for this fully general system when there's holding costs, and also for this fully general system when you have time varying arrival rate, holding costs or no holding costs. So that's a nice asymptotic result to think about. Another open problem is I showed you some numerics to suggest that the suboptimality gap between the C mu theta rule and the true optimal rule is not too large, but I can't bound that. So it'd be nice to have some bounds or something more on the convergence rate, kind of like Peter's question. Another open problem is maybe you want to learn the exact optimal policy, not an asymptotically optimal one. So you have a pretty large state space to explore. So that might be interesting to think about. And in that regard, maybe you want to just straight think about the cost. Maybe you don't want to think about sort of learning this, because I'm kind of saying, okay, I'm going to learn the parameters and then I'm going to learn a parameterized policy because I know something about the structure. But maybe another way to look at this is I'm just going to try to learn the right actions. I'm not going to try to have this nice structural form for the policy. Maybe another open problem, and those of you that were there in the panel discussion, this open problem is exactly what I was thinking about. There's a nice paper by Calvin and Devi, and it's in a matching world, and they have to learn parameters, but they also have to learn the classes. And so I think we have situations where, you know, there's something going on in the background that is some kind of algorithm to classify what customers are put in what classes, and then you have to decide the scheduling. So there's really kind of a problem where you don't know the classes and you don't know the parameters. And I guess another natural thing to think about is multiple pools of servers. We had a situation where all servers could serve all customer classes. But if I think about Rhonda's talk earlier this morning, there's certainly not you might need to divide this. You might want to divide the servers into different pools. Okay, so my last remark to lead you with is I think one key idea for these learning problems in stochastic systems that I think theoreticians and people that like asymptotic analysis can contribute to is we can exploit this asymptotic analysis to define an easier learning problem. And I did it in this one particular situation of a mini server queue with abandonments. But I feel like this idea that I'm going to exploit some of the beautiful asymptotic results we have in this community to tell me that I know something about the structure of the policy. And because I know something about the structure of a policy, I have kind of an easier learning problem. I don't think this is the only system where it can be applied. So, okay, so with that, let me ask if there are any questions, and let me thank you for being here.